literally an order of magnitude in complexity in the simulations, and I'm not aware of any realistic quantum transport simulations that rigorously include that effect. But what I would tell you is the following. As long as the electron density remains relatively low, the electron-electron scattering is going to be less important than when the electron density becomes very, very high. If it's very, very high, and you're looking at a resonant tunneling effect like this, obviously the electron-electron scattering qualitatively has the effect of broadening the energetic distribution. And so it will tend to wash out the negative differential resistance qualitatively.
Any other questions?
Yeah, go ahead.
Can this Wigner transport formalism be really fast to simulate, I don't know, like 2G or 3G MOSFETs and in the industrial devices, or it's still quite slow?
That's a very, very good question, and I would argue the following. I found a couple ways to make it very, very fast. Very, very fast. The devices that I'm interested personally in studying, and the ones that I'm funded to study, which is probably the more important of the two considerations, are predominantly one-dimensional in nature. But that's a very, very good question, and I would say yes. There are ways of making it efficient for 2D. For 3D, I'd really have to scratch my head long and hard about that. But I'll tell you, there are different approaches to it. If you give me the opportunity to work on a 100,000 core machine, like the guys at NNC and at Purdue use, then my answer to your question regarding 2 and 3D is yes. But that's not maybe such an interesting answer to your question, because probably a very small fraction of 1% of the research community has access to petascale computation. And so even though that might be an interesting result for one person at Purdue who has maybe 1 hour of time every week to simulate on that machine, it's not representative of what can be done in the general community.
Can you explain traveling dipole, the relation between traveling dipole and oscillation?
Yeah, sure.
Are they related to each other?
Yeah, okay, so the question was, are the concepts of a traveling dipole domain and oscillation related to one another? And the answer is yes. Well, so let me just backtrack a little bit, since I see I have some time, and discuss what constitutes a dipole instability in the first place. Well, a dipole instability will happen can happen in a material that exhibits negative differential drift velocity if electrons in that material have a larger average drift velocity at a lower field strength and a higher average drift velocity at a lower field strength and a lower average drift velocity at a higher field strength. Why does that happen? Because whether it's due to intentional nucleation at a field spike using the field crowding effect, like I've chosen to exploit, or whether it's nucleated at a sharp gradient in doping density, which is what is usually done for gun diodes, or if a depletion of local depletion of electrons is affected just by some random fluctuation. What happens is, in the depleted region, you have essentially positive excess charge, and that charge is positive. In the accumulation region behind it, the excess charge is negative. You induce a little tiny dipole. When you induce a dipole, that means the electric field in that direction within that dipole is higher than everywhere else, which means that the electric field everywhere else in the device is lowered. And so what happens is, at the lower fields everywhere else in the device, electrons will rush to get away from the region of that dipole. So especially on the front side, the leading edge of that dipole, electrons in the lower field region will escape the region of the dipole at very high speeds. Meanwhile, electrons on the back end of the dipole in the accumulation region, they plunge into the accumulation region at very low speeds. But what then happens is, as electrons in the leading edge of the depletion region are depleted more and more, that sucks the dipole along with it. And so the dipole will start moving until it's reached its full size. And that dipole will move with a certain velocity. Usually the velocity is more or less constant. It'll move from the point of nucleation with a more or less constant velocity all the way up to the anode where the electrons participating in that dipole instability are collected. Okay? When the dipole domain, specifically the accumulation layer, impinges on that electrode, it causes an instantaneous spike in the current. Okay? And once that happens, the dipole is gone, and now the electrostatic potential is dropped more or less as it was before the dipole throughout the device. Meaning, in the case of my device, where we have the field crowding below the drain edge of the gate electrode, we have that huge field spike, which then is going to nucleate yet another dipole instability, which will also start moving. Okay? And we'll have another spike in the terminal current, the drain current, let's say capital T seconds later. And when you have a pulse train of these spikes in current separated by time t, that represents a source of, in this case, millimeter wave or low-end terahertz radiation. You can imagine embedding this in a resonant circuit so that it will actually pick out one frequency at the resonant frequency of the circuit. So that's the origin of the oscillations. Okay. So the exact same principle conceptually as with the gun diode, GUNN.
Okay. It's almost 1. Let's thank the speaker again and enjoy.
All right, thank you very much. Thank you. Yeah.
Okay, so
All right, very good.
so let's say